Now what we're going to do is we're going to look at two reactions that go by free radical mechanisms. There's really only two basic reactions in this chapter. The first one is a completely new reaction that we haven't studied before. It's called free radical halogenation reaction. This is the observed reaction. I'm going to have a comment about how we might want to write this a little bit later. But for right now, what I want you to notice is we start with a carbon-hydrogen bond. And in general, most of the time, although not always, we start with just an alkane. In other words, we have no double bonds. We have no triple bonds, no alcohols, anything, just carbon and hydrogen single bonds. And what we're going to do is focus on one of the hydrogens in that alkane. We're going to react that with X2. Now remember that X is our symbol for halogens. In this case, it turns out because of the energetics of this reaction, because of the way the delta H works, it's really only safe or useful to use either Cl2 chlorine or Br2 bromine. The fluorine does react, but it reacts violently. It gives off so much potential energy that it's explosive. And iodine, it turns out, has such a low reaction or such bad energetics that it reacts slowly, and it even can break off and in theory reverse. So we don't want to do that one. We are also going to put in energy in order to make this reaction start running. Now we don't have to put in energy continuously. It turns out we just need energy to get the reaction started, but often we do put it in continuously. We can put energy into reaction in one of two ways. We can either heat the reaction, or we can put in light of the proper wavelength, because the energy of a photon of light is equal to h nu, right? Depending on the wavelength or frequency of light. So organic chemists have developed a symbol to indicate that we're putting in either heat or light. So we use delta for heat, which is actually a symbol that we used for heat in general chemistry. And for light, we actually use h nu, which is E equals h nu, right? So you will see one of these two usually written under the arrow or next to the reagent in the observed reaction for free radical halogenation. Our product then is going to be a product where we have replaced one of the hydrogens with the halogen. Now, here's the thing. It turns out that what we get in this reaction, we also get a byproduct where the hydrogen that was replaced is now attached to the other halogen. And most of the time, we ignore byproducts. But it turns out if we're calculating the energy changes for the reaction, we need to make sure to put all of the reactants in and all of the products, including the byproducts, or else our energy change will be inaccurate. Where this creates a problem is that you know how organic chemists typically write reactions where we write the carbon piece as the actual reactant, and we write the other reactants as things that change the carbon piece over the arrow. Technically, this halogen should be written as a reactant. And when we are calculating the, the delta H change for this reaction, we're going to need to remember to put this in as a reactant and include its bond association energy. I'll show you that either later in this lecture or in lecture on Tuesday. Okay, so we're now going to look at the mechanism of this reaction. Free radical reactions have a very special mechanism. Only free radical reactions do this kind of mechanism. Make sure that if you're going to write this mechanism, you know 100% that it is a free radical reaction. So in free radical reactions, the elementary reactions, there's several of them, but they're divided into three basic types. The first type is what are called initiation steps. Initiation steps start the free radical reaction. They start by breaking bonds homolytically to form free radicals so that the radicals can react. Generally, in order for this to occur, we have to have something in there that has a relatively weak bond, a bond that can be broken with a small amount of potential energy added. In our particular free radical halogenation reaction, it's the halogen that has a weak bond. If we look on the bond association energy, the table, the bond association energy for these bonds ranges from 60-ish down to about mid-30s. In comparison, the bond association energy for carbon-carbon and carbon-hydrogen bonds are in the 80 to 100 range. So it takes a lot more energy to break a carbon-hydrogen or carbon-carbon bond than it does to break one of these halogen bonds. We believe that the reason why these halogen bonds are so weak is because of all the lone pairs on the individual halogen atoms. Those lone pairs are repelling each other, pushing that bond apart, making it longer than it would otherwise like to be, and increasing its inherent amount of potential energy so that we don't have to add much more to break it. So we start with our halogen, we put in heat or light, that's going to provide our energy to break that bond. And what we see is the bond breaks homolytically. So as the bond breaks, there's 2 electrons here. So I've rewritten it down here so you can see the 2 electrons. And we see that 1 electron goes onto one of the atoms and the other electron goes onto the other atom. Now, since only 1 electron is moving, we don't use our double-headed mechanism arrows. Instead, we use this single-headed arrow, which we often call a fishhook arrow. And what I do generally, especially on these, is I try to make the fishhook arrows on opposite sides of the bond. Like this is on the top going here, this is on the bottom going there, just to keep them out of the way. But in theory, you could do both of them on the same side. If we do this, then the result would be 2 halogen radicals with a single electron on each. This is then written with all the lone pairs. In general, I'm going to tell you that when we write these out, we usually stop writing the lone pairs so that we can very clearly see the single electron standing out from the rest of the lone pairs. Now, initiation steps are very rare in a free radical reaction. Typically, we're going to have 1 initiation step for every 1,000 of the propagation steps, which is the next one that create all the products, in the gas phase at room temperature. The rarity of the different types of free radical reactions depends on the temperature, and it also depends on the concentration of the radicals. Many of these are run in the gas phase, and the lower the pressure, the farther apart the radicals are, the longer their lifetime. The next steps are the propagation steps. Now, it's very important to note, and I'm going to say it again at the bottom, that the propagation steps are the steps that form the products. And in fact, if you have the correct propagation steps, those propagation steps should add up. If we put a line here and add these down, canceling things on both sides, they should add up to the overall observed reaction. There's way more propagation steps than there are initiation steps, and there's way more propagation steps than there are the steps that end the reaction, which we call termination steps, which we're going to look at in a little bit. So what we would see then is one of the radicals that we formed in initiation would come down. Now, radicals are lacking electrons and they're high potential energy. So what they want to do is find an electron somewhere. All of the bonds have electrons in them because bonds are made of electrons. So what radicals do is they take their radical, their single electron, and they pair it up and pull an electron out of a bond. But when they pull that electron out of the bond, they pull the atom with it. So by pulling the electron out of the bond, what that does is those electrons pair up and they make a new bond. So this halogen removed the hydrogen. So we would make a hydrogen to halogen bond. The other electron then comes out of the bond and moves on to the other atom. And that forms a carbon radical. So that's our first initiation step. Now we have a carbon radical. So that carbon radical is floating around. It's going to look around and it's going to find another molecule that it can pull electrons out of. Now, it could pull electrons out of another CH bond, but all that would do is create a CH here and a radical there and so forth. So the only other molecule that we have in a large quantity is our halogen. So it's going to find a different halogen from the one that broke apart. It's going to pull an electron out of that, pair it up with the electron from the halogen, forming CX, which is our product, right? Carbon to halogen, and then another carbon radical. And the problem is that this doesn't end the reaction because now we have a carbon radical, I'm sorry, a halogen radical that's unstable. So it's going to move down and repeat step one with a different molecule of our alkane reactant. And those two are going to repeat. And then we're going to move down and do it again and again and again. This is called a chain reaction. It's a reaction that just keeps repeating over and over again until something else happens to stop it. In general, again, at 1 atmosphere pressure, room temperature in the gas phase, this will repeat 10,000 times before it ends, on average. So we make a lot of product. Okay, so just to kind of help you sort of visualize this another way, I want you to think, we've talked a little bit about 99 molecules on the wall. And this is another example of where the way we write reactions can be very confusing because we write one of these, one of those, one of those, one of those, when we really mean a mole of these, a mole of those, and so forth, right? So going back up to the very beginning, just really quickly, when we write our observed reaction, this equation is indicating the relative proportion. So one portion of this, one portion of that, and so forth. But really, when we work with them, we put in like, a mole of these, a mole of those, and so forth. A mole is a very hard number to conceptualize. So I generally like to talk about 100. So we have 100 of these, we have 100 of those, we start with 100 of these and 100 of those, all mixed together, right? So then when we do our initiation step, we take one of the 100 halogens, we break it apart, we still have 99 halogens left. That broken halogen then finds one of our 100 alkane reactants and reacts, leaving us with 99. This then finds one of the 99 halogens that we had left, breaks it. So now we have only 98 of these, and we have one product, right? Then that halogen is going to find one of the 99 alkanes that we have left, react with it. Now we have 98 alkanes, and we have one of these, and we just keep repeating. So it's the 99 molecules of alkane, react with a halogen atom, make a carbon radical, 98 molecules of alkane left. 98 molecules of alkane react with a radical, form a carbon radical, 97 molecules of alkane left. That's the 99 molecules on the wall. That's what makes it hard to picture this. Now, this ultimately does end. It ends when a radical combines or is taken away by something else. In general, we call these ending steps termination because terminate means to end something, okay? And typically what we look at is the radicals combining to form bonds, because that would be the reverse of the bond association energy reaction, right? If you take one electron here, you put it together with one electron there, you form a covalent bond, that would release potential energy, that would be more stable. This would happen really often if they were super, super concentrated, but they're not. They're very rare. So that's why this doesn't happen very often. At any rate, what we do to figure out what the termination steps would be then is we go up to our propagation and we find all the radicals in our propagation. So we have a halogen radical and we have a carbon radical. We then imagine those combining in all possible combinations. So a halogen with another halogen, a halogen with a carbon with a carbon. These would be the termination steps. The book also talks about termination steps on the walls of the apparatus, which certainly is possible, but generally we ignore those. Okay, now the problem with this is that if you look at our middle termination step, do you see how that also forms one molecule of our carbon product? This really confuses people. They see this and they say, oh, okay, that's how we're making the product. And they ignore the fact that we make product here in our second propagation step. The important thing to note is that termination steps are very rare. There's only about one per 10,000 propagation steps. What that means is that we formed 10,000 molecules of product before we made even one this way. So this is a very rare occurrence. So we should not be writing this as a way that product is formed. We're only writing it as a way that the reaction chain ends. The other thing that's important, and this actually goes back to the very original research on this, which supported this mechanism, is to notice that actually in this reaction, one of these carbon radicals will combine with another carbon radical to make a larger alkane than the one we started with. So for example, if we did methane, we would be running this reaction and we would be forming very small amounts of ethane. And in fact, it was by very careful experimental work, the scientists who worked out this mechanism, the discovery of ethane in the products that were not present in the reactants, because initially they thought it was just a contaminant in the reactants, but they went back, they really purified the methane very carefully that there could be nothing else in there. They still saw ethane in the products. That was a clue that we must have something like this going on where two of the methanes are combining together. That's really strong evidence that the free radical mechanism looks like this. Okay.